the stupid decision and thought I'm going to drive to Koreatown from Santa Monica.
Okay, well, that's a bad one. Yeah.
So yeah.
That's a bad one. Then, yeah. But this is why we have audiobooks.
Right.
They moved. They have so many badges from Audible. You know, they give you sort of a badge if you are advancing. When I started teaching in Pasadena, suddenly I got so many more badges.
So when you drive, you have
yeah, it's when I was teaching at 7 o'clock at night, it takes me 2.5 hours from Santa Monica because it's the craziest time.
Right. And the train, you can't take it, or
no. I will probably have to be 3 tickets.
Yeah.
It's perfect here because from me, I mean, this just works really well. Getting here, but it was yeah, driving is. But it was nice. It's cooler.
Yeah, it wasn't much traffic, but like the water was insane. It was just like everything's flooded. And when you were driving on the leftmost lane, the leftmost lane on the other side, it's just like
slashes
of water on you.
Well, probably this is the last rain of the season, so that's it. 6 more years of no rain and then 1 day of rain. I would say 6 years from now. It's interesting how we'll actually get some flooding when the snow melts, because we should have a little bit more snow than usual. That might be fun as well. But that's it for water. Hey, good to see you. So good to see you.
All right. So let's quickly recap what we had talked about last week on Wednesday, and basically we just introduced like how we deal with supervised machine learning problems, and like what the data looks like, what the objectives are, and what a hypothesis and a hypothesis space are. And today we're going to go a little bit deeper into that and like define like what the basic power of these hypothesis spaces are, and just a little bit more of statistical learning theory, where just to give you a flavor that there is actually theoretical machine learning out there that is concerned with, for example, trying to find like what is the right size of a training set for a certain problem to have a like minimum expected error with a maximum or like large expected precision or like certainty. And so we talked about positive examples, so like we denote those as pluses in the middle there, and negative examples are kind of like surrounded around there. Our input is defined by these 2 input dimensions, x1 and x2. So we have like price and engine, power as our inputs, and we defined like, okay, we need to basically find the target labels, which are coded in this case as 0s and 1s. So our training data, and like again, you will have this in most of your tasks when you do machine learning, or in particular with supervised machine learning, is basically you have an input and the output tuple, and you can use this output tuple, for example, both for training but also for evaluation, etc. Of your machine learning algorithm. Okay, so we had discussed that at length, and we then defined, okay, so this is our class that we actually want to find, but as in most machine learning experiments, we do not know exactly what the shape or what the hypothesis or like the target class is, because that's hidden, and we have to infer this from our training data. So the target class is family car, and the hypothesis or this family car is actually defined by these 4 threshold parameters, so that these are kind of like supporting a rectangle in this world. So if we know kind of like what the hypothesis probably will look like in our case. So in this case, it's a rectangle. We can, for example, define a hypothesis space, which could be all other rectangles in this two-dimensional space. Okay. We could also define, say, well, our hypothesis space is just a line or a threshold on that goes through this space, and obviously that would result in a little bit of a problem because we don't have enough expressivity. We cannot express this class properly with just a line drawn through this space. Okay, we might be able to do it with, I don't know, maybe like 3 lines, but you would have to try to find. Yeah, I think you can do it with 3 lines, but that also already kind of defines a new hypothesis space, which could be triangles, and so this is the different types of expressivity that you have with your configurations is basically important to know. So we define our hypothesis space as all rectangles, and we just want to find a rectangle that fits our hypothesis or our data set here. And as you can imagine, there are many of those, and we discussed how these can be learned, or what these can be, and so we want to approximate this class C, and we want to find the hypothesis that is most of the time correct. And we said that there are multiple ones of those that we can find. So we had the S class here, or the S rectangle hypothesis, which is the most specific hypothesis, and the G one, which is the most general hypothesis. Out of those hypotheses in this hypothesis space that do not make a mistake on the training data, okay? So that is clear, right? You can define a much wider one, but it would make mistakes on the training data. And so then we discussed, okay, what would make a good or a better hypothesis than this very specific one, S, or the very general one, G. And we talked about the impact of noise and what noise does to our data. It moves it a little bit around, and if you have the most specific one, well, you don't have a lot of wiggle room around the positive class, and if you have the most general one, you don't have a lot of wiggle room around the negative class, so or negative observation. So what we want to do is we want to kind of find something in between that basically maximizes, for example, the margin, which is defined as the space between the hypothesis or the decision boundary and the nearest example on either side. So 2 margin wides is the entire width of this, or the entire wiggle room that we have. Okay, so, but then we also had a problem where we said, okay, if we just define our error by counting pluses and minuses in our training, so if we make an error and this one, for example, would be classified as negative, or this one would be, for example, classified as positive, if we just count these as +1, +1, or minus, as number of errors, then we cannot find this optimal hyperplane, or this optimal hypothesis that maximizes the margin. So what we needed to do, does anybody remember that? We needed to update the error function. And the important update to that error function is to not just count binary-wise, count errors as 1 or 0, but to count them with a certain level, or a little fuzziness to it. So basically we need to know the distance of each point to the hyperplane. Okay, so it's not just plus or minus, it's the distance. Okay, so that's important. And we're gonna find out how to optimize these hyperplanes and find or define a class of maximum margin classifiers when we get towards discussing support vector machines. And those support vector machines have been really popular because they do or have this property where they maximize the margin. And that can be very useful if your data is a bit uncertain, if you don't have too many data points, and if you want to kind of also have a quick way to evaluate your system, because in the end, and we talked about this a little bit as well, in the end, if you want to try to find this hyperplane or this hypothesis H here that maximizes the margin on all the sides, you do not care about these white data points. You only care about the gray ones, and these are the support vectors. So they hold up this hypothesis. If any one of these changes, the margin moves, or like the hyperplane changes, and it's not optimal anymore. But if you remove any of those white ones, nothing changes. Okay? So that should be clear. All right. So that was enough for recapping. Are there any questions for what we did last week? No?
But I have a question from this about this.
Okay. Yeah.
So why do we want to have the margin to be, when we are doing SVM, I always had this question, so that why are we trying to make the distance the same between different vector points, support vector points?
Yeah.
For example, if we have, right now we have rectangular shape, right?
Yeah.
But if we have circular shape, like all the positives are in the middle, right, and they are really dense, and maybe one point, one negative point is close to these positives.
Yeah.
So the density of the positive points is more important. I mean, I want to have more space between, from the border to positives and negatives.
Yeah. It's a very good question, actually. The answer is, like, it's easier to optimize, and there are some investigations going in towards, like, then changing that towards, so you can have it closer, you can have the hyperplane closer to one class or the other, but you can also learn that. So and in most of the examples that will happen in real world, you don't really find a perfect separation anyways. You will always have data points from one class falling into the wrong side of the margin, or falling into the margin, or even on the wrong side of the hyperplane. So you'll always have some training errors. And if you have real-world examples and you do not have this, like everything is correctly classified, you have like a 100% correct, you probably overfit your problem. Like there's hardly any problem where you would expect this condition, as I showed in this figure, to perfectly hold true. And we'll discuss that in detail when we talk about support vector machines. But there's, you have to fine tune between how accurate do you want to be on your training set, and how generalizing, or how well you want to generalize, and how many parameters you want to fit, or like how many support vectors you want to find. You don't want to find, so in the worst case, you find every data point in your data set is a support vector. So you set up, you set up this very, very complex separation.
That's overfitting.
Yeah, that's completely overfitting, right? And so you don't want that. But yeah, there's a couple of things that need to be considered. But you can learn this, yeah.
So you mean the distance, the ratio of the distance can also be a parameter to be learned?
Yeah. Yeah.
Is it in SVM, is it a parameter to be learned? Or no, we are trying?
Not in the simple versions, no.
Okay.
Yeah. We have worked on fuzzy support vector machines where you basically, I can talk about this in the class as well, but basically every data point doesn't just belong to a class, but to all classes with different membership assignments. So that happens most of the time if you think about human behavior. Like if I have a certain behavior and you look at it, many people can have different opinions. So you could say, oh, he looks frustrated, but a different person could say, no, but actually he's frustrated, but with a little bit of anger in there. But some person might be completely out of their mind and say, oh no, he looks happy, right? And so these different opinions you can leverage these different opinions of human behavior, for example, and you can use those also to find out, and then you would have these parameters or like the data points falling into all the classes at the same time. You want to optimize this join thing, but it's very specific. So yeah, probably like little bit beyond from the second week. Yeah, but we're gonna come to these supervised machines. We can talk a little bit more about that then. All right. So, any other questions? All right. So let's talk a little bit about statistical learning theory then. And basically, I would like to introduce basically two concepts in statistical learning theory. The first concept is VC dimension, which stands for Plotnik-Chervonenkis dimension. And basically what that says, or what that investigates, is basically we want to know in a data set that contains n samples, in this case for example, it's 3 samples. So this is a data set, this is a data set, and so on, okay? So we have 8 different data sets. And for a data set with 3 samples, we have 2 to the power of n many ways to label the data. So you can see this here, right? So you have 2 blue, 1 red, 1 blue, 2 red, 2 red, 1 blue, and a different configuration. You can have all reds, all blues, okay? So you can label this data set in many different kinds of ways, right? And so we can define 2 to the power of n many learning problems through those data points, okay? So what we want to find now is basically the simplest classifier that can classify all of these data points, or like all of these 2 to the power of n many classification problems, okay? So we could define, for example, a circle that entangles the blue ones, okay? But maybe a circle is already too complex, or we don't really want that, or and it might not be the most efficient solution. And a circle might actually be more powerful and could, for example, maybe like classify 2 to the power of 4 many different kinds of problems, okay? So there are many differences here, okay? So this is kind of like the task that we want to solve. And maybe somebody already sees like what classifier or what hypothesis space would basically be able to solve all these problems here.
Align.
Align, that's a good one.
But the question is, this is 2 to the n, it should be k to the n, because now we have classifier that gives only binary.
Yeah, it's only binary.
Binary, but
This is
if
only
we
binary.
have 3,
No,
that would
that's-
be 3 to the n.
Yeah, it's different. Yeah.
It's different?
Yeah.
It's not even 3 to the n?
No, it's
Uh-huh.
just,
Okay.
yeah. It's just
So
binary clusters.
So just
And then
binary.
we had that last week, right,
Mhm.
where we said if you have multiple class problems, you can always like break that down into one versus all kind of classifications. So like it's not. So this is not like restricting the generalization, but it's just you have to define it as a binary class problem. Yeah. Okay. So
So it's k over n, right? Because these are combinations, no, these are permutations,
yeah.
right?
Yeah.
So that's why it's not 3 to the n, okay,
Right.
I think we
Oh, why do they say this is a model used by perceptrons? Is
Sorry?
it a model used by perceptrons?
So you can test the power of a perceptron using this kind of
Okay.
approach. So the VC dimension basically gives you an idea of like the discriminative power of a certain type of hypothesis class, or like the perceptron or line or rectangles and so on. Okay.
Okay.
So, and if it is possible to find any learning like any, and it's not like every, but one, okay? And there's a big difference because, so the difference is because I can always come up with a problem that's like artificially construed and you cannot split. So if you have 3 data points in a perfect line, right, and you have a line only available, I cannot classify this, right? I cannot properly find anything that splits the classes properly, okay? So I can always come up with a problem that's like construed in a way that doesn't allow this to happen, but it just needs to, like, there needs to be one sample, okay, of the data set. So not every sample, okay? So, so if I can find a problem where I can color the points in any which way I want, and I still can classify this with a error of 0 on this data set, then the hypothesis class H shatters, shatters this data set, okay? And if it if any of these problems can be solved by hypothesis H in the hypothesis space capital H, then capital H shatters the n data points, okay? And the maximum number of points that can be shattered by H is called the Vapnik-Scherer dimension, or short VC dimension, okay? And so we need to find the maximum number of data points that a hypothesis class, like a line, can solve with 0 error. And we don't have to find all the configurations of these 3 data points, but one, okay? We just need to find one. So let's look at an example. Basically, for the 3 data points, that works, right? That works, that works, that works, that works, that works, that works, and that works, okay? So we know at least the Vapnik-Scherer dimension of a line is 3, right? But is it 4?
It's impossible.
Right? And so it's not, like, it's not 4, it is 3, because I cannot find any 4 points. You can try that out, like, you can locate them wherever you want. If you color them in these different ways, you cannot find a configuration of these 4 data points that are solved, like where a line solves this problem, okay? So this is important. And what about, let's say, what other, so like what's this, the VC dimension of a 2D line? Well, it's 3, we just heard that, right? What would it be of a rectangle? Can we find a rectangle that solves like all 4 data points? We can try that out. Alright, so
So, I'm sorry, but what about the example you just mentioned? That
Yeah.
all the 3 points were in the same line. Don't we consider that?
yeah, so you don't have to find, like, you don't have to solve every single configuration, but you have to find one solution for 4 points, or for 3 points.
So for 4 points, I mean, if 2 of them are here, 2 of them are here, we can separate them by a line.
Yeah, we can. So, okay, so we can separate those, right?
The definition of VC.
But if we, no, but you have to have the 4 locations, but then you have to solve all the,
Okay, the location is important.
the location stays,
Right.
but the coloring or the permutation of them changes, okay? So I cannot solve this,
Okay.
and there are no 4 points that I can find where a 2D line can solve this problem.
So we look at the location, if there is one type of labeling that this, I mean, specific shape, like a 2D line, can separate it, the dimensionality is gonna be applied, right?
Right.
It's gonna do it.
Right.
Okay.
Yeah. So, but if I have 4 points, and I can put them in any way I want to, and I want to find a rectangle that splits all of them, well, I can do that. So I can do this, I can do that, I can maybe do this, I can do that, I can do this, I can do that, right? And so with rectangles you can solve 4. Okay.
Sorry, for 4 points, if you have a curve that goes to just like you will actually be able to solve that condition.
Which, so what, like data points like this? Or,
If you have a curve that can like.
ah,
is that-
yeah, okay. Right. Good point. So let's do this. So if you have 4 points, and you have a curve, so you can have something like this. You can have something like that.
Yeah, that would actually be able
Yeah.
to solve that.
So yes, but this curve has more than one parameter, right?
Yes, sir.
It has an x and an x square.
Uh-huh.
So yeah, exactly. Like you can solve that, but not with a straight line.
Okay, so
Right.
line here means straight line.
Yeah, yeah. That's a very good point. Yeah. Yeah, that needs to be defined as like a linear solution, a linear line with like a bias parameter and like a steepness parameter of like a y. Yeah. Okay. So for rectangles we can solve for.
So it doesn't really matter how many rectangles we have, we are still solving it by having 6 rectangles.
No.
No.
Yeah. So you label it. You just label every time, and these are always the 3 same data points, right? But you just have to label them in all possible configurations.
Right, but if we have 4 points, it's probably not going to be shattered by a single rectangle.
Yeah, it is.
It is?
Yeah.
Always?
Yeah.
For 4 data points.
Yeah.
Unless they're in line.
Yeah, but that you don't have
No,
to solve
well,
all of them. You just solve one
Uh-huh.
problem, right? And the interesting part is like for rectangles, there are no 5 points that you can shatter. Like that, it's impossible, and it's kind of interesting, because you can always like find that middle point that where you have to like draw around to capture the other guy, but like you can't. And so yeah, that's kind of like the interesting solution. And then so we had rectangle. So 2D line cannot solve this problem, but a rectangle can. And it's yeah. If you start trying it out yourself, it makes more sense. And you cannot find 5 points for a rectangle. But then the question really is like, what about neural networks? What about complex systems, like where you have many parameters, like 1 million parameters? Well, I tried to find a little bit of an answer for this, and like a more digestible answer than the answer that I know is happening. And the most digestible one that I found was actually from the original paper, or it's not the original paper, but it's an older paper where they came up with this theorem where we actually tried to learn this function here, and it's a plus minus valued function, and like each input can be in R, so that's nice, and the algorithm that is computing is limited to this number of operations, so it plus minus times divided, and it also can have these jump conditions where it's greater, equal, and so on, right? And the output is 0 and 1. And the interesting part is that, well, the Viterbi next dimension is smaller or equal 4 times the number of parameters and operations it can do times t plus 2. And then if you want to go even further, for 2-layered neural networks, you find that the Viterbi dimension is defined by an O parameter. So it's like in this class of numbers, okay, so it could be infinity. But it doesn't grow with exponential power, right? So it grows with a log linear kind of function, okay, so it asymptotes and so on. So like it's very hard to define the Viterbi dimension for like real world machine learning algorithms. But kind of like the gist of this is for practical machine learning algorithms, it is difficult to assess it exactly, if not impossible, but upper boundaries can usually be given. So you can have kind of like an idea of, am I going to be able to classify any problem with number of data points x or n with this kind of machine learning algorithm. So just like as an introduction to this kind of idea of computation. Does that make sense? Right. Cool. So just as a summary, VC dimension provides a measure of expressiveness, or the power of a hypothesis space, and you can start classifying, or you can arrange these hypothesis spaces with their power or their expressiveness. So you have the most simple one would be what? Like if you have a 1D thing, it's a threshold, right? Like 1, and that only shatters 1 data point, because if you have 2, you already, well, can you do 2? I guess you can do 2. Yeah. So 2 data points you can shatter with just 1 number at the threshold, but not 3. You can have the middle one as a 1. So in a one-dimensional space, you always have everything on a line, right? So that's a problem. And then, so points, lines, rectangles, logical functions, neural networks, etc. So you can rank them kind of like in their power. And the VC dimension is the maximum number of data points that are shattered by the hypothesis space. And the wording about what shatters means is important. Yeah.
So I was wondering, what is the point of testing all the combinations that are possible by the data points? Because when you generally have a data set, it's going to be just that one data set. I mean,
right.
The distribution of the data is not going to change at all.
And that's something I want to get to in a second. Luckily, we don't have to shatter data sets, and you will quickly see that a much simpler neural network will be able to express a natural data set than the number of data points are in there, or would have to be shattered. If you try to come up with a network that is has sufficient VC dimension for a number, if you have 1,000 data points, you want to have VC dimension of 1,000, something like that, right? But that's not realistic, because thankfully the world is smooth, and data points that are neighboring are often not in different classes, but they're in the same class because the world is smooth, and we have basically a Gaussian over every feature dimension. So that makes it a lot easier for us. So we don't have to do this. This is just for a theoretical construct. Okay. So that's the saving grace, so to say. And so yeah, for more complex ones, we can find upper boundaries that are provided and not the exact VC dimension that is calculated. This is exactly the point. So the VC dimension is independent from the probability distribution that your data is pulled from. So you can have any labeling in your data set. But luckily, in real world examples, neighboring samples often have the same label, and we do not need to shatter the data set. We don't have to worry too much about this, okay? But it gives you a framework to think about, what is the right hypothesis space for a certain problem, okay? Yeah. All right. So any questions to VC dimension?
Yes. So VC dimension is kind of the opposite of the capacity of the curve.
The capacity of the curve.
Well, yes. Capacity of the curve is how many. Basically, what I was reading in the textbook, it says that it's how many data points you can shatter, right?
Right.
So VC dimension is, because it's the maximum number, it's well, no, then it's not the opposite. It's
Yeah. No, it shouldn't be. So you mean if you have a curve that has to fit a number of data points?
Yes.
So yeah, so it is kind of directly related to that. If you have a problem that is data points with a value and a target, and you want to fit a line through all of them, so you want to make a regression problem, right? The more parameters in your curve you have, the more accurate you can fit those, but you might not generalize well. So your the VC dimension of a high like high order magnitude polynomial function is a lot larger than for like a first order. So we just had that first order like a line, a straight line shadows 3,
Yeah,
but
this one will be,
like a second order shadows 4 possibly. I don't know if it's 5. I don't think it does 5.
So we would use VC dimension basically to figure out the capacity, but the world is smooth, so we're not necessarily using it directly like that.
Right. Yeah.
Okay, I will need to think about it, sorry.
It's not the
Just-
so VC dimension is kind of like defined for classification, not so much for regression.
Okay.
But for regression, you can imagine like if you have more parameters, you can fit at your data set much better with a much smaller error, but you might not generalize. Like you might have a problem of overfitting there. And the same holds for this kind of class. Okay.
I have questions like, can we do the VC dimension after the clustering? For example, like we do k-means clustering, and maybe we can separate the samples into 3 groups. Does that mean like we can use DC dimension to separate the samples by line?
So if you do k-means classification, or k-means clustering, you try to you find these prototypes that fit into your data set, right? So you have like a cluster center here, a cluster center there, a cluster center here. But that doesn't really give you well, you can use that to assume labels for your data points. Say like, okay, all the data points that fall into this cluster are class 1, class 2, class 3, and then you can try to find separation hyperplanes for that. But I wouldn't wouldn't directly see the use for a VC dimension classification, or use case for needing to know the VC dimension of certain hypothesis space to label the k-means, because you already kind of did it, right? Yeah, I'm unsure how to answer that question. Okay, and then so very briefly also another theoretical concept that comes up in statistical learning theory is the probably approximately correct learning, so PAC learning. And basically the goals of this are we want to find a hypothesis that is approximately correct. So we want to find a solution to a certain data set problem that has an error probability that is bound by some value. So we can arbitrarily choose that value too, right? You can say we want that error to be just a little bit above 0, or we can say, okay, we want that to be 15–20%, right? We can say that. And we also want to have high confidence in the hypothesis that it is correct most of the time. So that means that the hypothesis should be probably correct by a specified probability. So we want to have this error that is smaller, but we also want to have this error a certain number of times. So that at that certain number of times should be 80% of the time my hypothesis will have an error smaller than 15%. Okay, so that could be, for example, a definition of that. And what the actual kind of mindset behind that is we want to not just have a good classifier, but we also want to know how many data points we would need to be able to find that. Okay, so that's the main idea. We want to know how big our data set should be and how good our data set should be. It should always be representative of the actual data that comes in once we are in a runtime, or when we deploy our data set or our machine learning classifier. We also want to know how many data points we need to train that. Okay, so if we have a target class C and examples x drawn from an unknown distribution p of x, we want to find the number of samples n such that with probability of at least 1 minus delta, so this is our confidence, the hypothesis H has an error of at most epsilon, and that's our error probability, okay? So we want, for arbitrary deltas, less than a half an epsilon greater or equal 0, right? Equal 0 is a bit difficult, but so this is kind of like the idea, okay? So we want to have the probability high, so this should be small, and epsilon should also be small, okay? And then, so this error probability would then be this probability of the difference between the hypothesis, like the actual class and the hypothesis that we have should be smaller or equal than epsilon, and this whole thing should be greater or equal than 1 minus delta, okay? And so this is the region difference between C and H, and this like becomes more clear on the next slide. But basically the region difference are all these 4 strips here. This is one strip, this is one strip, this is one strip, and so on, okay? So this is the actual class C, and that would be our hypothesis, right? And so we want this space around to be smaller than or at maximum epsilon, okay? So what we need to do is that every strip is not larger than epsilon divided by 4, because there are 4 strips, okay? And then, and the probability that a drawn sample misses the strip is 1 minus epsilon divided by 4, okay? And so that a probability of n independent drawn samples miss all 4 strips would be this function there, okay? So, and this we define as our delta. So most of the, like this is our error probability that that n samples don't fall into any of the 4 strips, okay? So it's just kind of like giving you a little bit of a geometrical evaluation of like how we would do this. And basically, we then have this function to be less or equal than delta, and with this inequality expression, we can now pull down the n and know that we need at least that many samples to fulfill this problem, okay? And you can already see that the number of n will grow the smaller these guys get. Okay, so if we want to have an arbitrarily small error of like just 1% of error, this number becomes very large, and then this number becomes also large. Okay.
So a quick question, what does the epsilon mean again?
So this is the likelihood of making a mistake.
This.
Yeah, so this would be, the epsilon is the likelihood that a data point from the positive class falls into this strip, where we only classify, because this is our hypothesis, we only classify everything that's within this smaller rectangle as ones, but epsilon is the probability that a drawn sample falls in here, which is the actual class, within the actual class, but outside our hypothesis. So the closer we are to C, the less probability we have that the data points fall into that range, okay? So yeah, so the difficulty is like if we want this to be very small and our like certainty that we make no mistake or we have this actually small error also makes this very large. So like the problem really is that the more accurate you want to be with the higher confidence, the more data points you'll need, okay? So it becomes more and more expensive to be low error and high confidence, okay? That's kind of like the idea there.
So if our hypothesis space is not a rectangle, but let's say a circle,
Yep.
then we will not have 4 strips. We
No.
will have a radius minus
Right.
whatever, right?
Yeah.
So the whole formula will need to look a little bit different.
Yeah, it will look a little bit different, yeah.
And if we have a polynomial curve,
Right.
then or a hyperplane,
Yeah.
then it goes crazy to calculate.
Yeah,
that
we just
number.
have to
But
define.
would this be good enough to kind of eyeball, because we will never, right, we are now talking about how many samples we need in data set.
Right.
And we don't know what our classifier hypothesis space will be, so would this be approximate enough to eyeball and say, well, we need 3,000, no, we need 4,000?
And so it
Even
doesn't,
though
yeah.
our function
So
is super
it doesn't give you like, oh, we need exactly 3,450 data points, but it gives you like levels of magnitude.
Mhm.
Like, do I need 100? Do I need 1,000? Do I need
Right, right, right.
10,000 or 100,000?
So
it's
we
kind of
can, we can just stay with the rectangle, disregard
Yeah,
completely
like,
the complexity that will happen on our hypothesis hyperplane.
right. So like, and with the rectangle also, like, not all strips are the same size, so we kind of arbitrarily chose
Yeah,
this as a solution. What you would, in a sense, do is, like, you would try out with different classifiers. Like, you would try, you would try to, like, assess, like, what's the error with how many times. So you kind of try to get a feel for that.
so we would not have to do, let's say, an estimate of how many actual permutations of the problem there are. Let's say that we have
Yeah.
3 parameters that we are tracking, simple thing. And then we can say that it's 3 over 2, whatever, however we are drawing it. Then we say out of that we need a percentage.
Yeah.
We can use this.
So, for this problem, you wouldn't label the data points differently. For this problem, you would draw different subsets from your data set and try out, like, how to classify.
Okay.
Yeah. Okay. Right. Other questions? So take a 10-minute break. Back at 11, or like, let's see, yeah, 11 is good, and then we can continue with some regression, and I will keep. So the slides are online, but I keep the machine learning experiment discussion and evaluation for Wednesday. So it's